Hi, everyone. Welcome to our weekly seminar at Jagiellonian. Today, our speaker is Sergey Norin from McGill. Sergey is already some years there at McGill. I'm actually not sure how many, but for me, it's like forever. I checked that you were before at Princeton and at Georgia Tech, where you graduated. Well, Sergey is a very active member of our research community, and research that I know is centered around graph theory, but both sides, extremal and structural. Today, we definitely will see some structural part, and with non-trivial machinery. Actually, I know some papers of yours using algebraic stuff, but today it's I know this is Gromov theorem, so some topology. We are very glad that you came here today, Sergey, and please go on. The floor is yours.
Okay. Thank you very much. Thank you for inviting me. Thank you, Pat, for kind introduction. So today I will talk about a work which started at a Banff workshop on graph product structure theory in November last year, mostly motivated by trying to understand stack numbers of products of graphs. This work eventually involved topological tools, and now we were trying to understand these topological tools, and I've been thinking about it even further, and now I want to present to you in particular different motivation for the toolkit which we use. In particular, I'll try to actually remove reliance on Gromov's theorem in some sense that Piotr mentioned. So this work started at this Banff workshop, and it's joined with David Epstein, Robert Hickenbotham, Laura Merker, Michael Severin, and David Wood. It was my first live workshop since COVID started, and I was actually the fortunate one. Out of all these courses that collaborated at the workshop, only I was physically in Banff. Everybody else was online somewhere else. Okay, so the main goal of this talk is to try to sell you on the higher dimensional, primarily two-dimensional notion of a Bramble. I want to show that it's useful. And so, of course, the story will start with the usual Brambles and graphs, and those are motivated by tree decompositions. So I will need a definition of tree decomposition. So a tree decomposition of a graph represents somehow a graph by its image on a tree, where each vertex is mapped to a set of vertices in a tree, to a connected subgraph of it. And the requirement is that if two vertices are joined by an edge, then the subgraphs, subtrees representing those vertices must intersect. So as a result, each vertex in a tree gets assigned a bag, a collection of vertices of the original graph. So, I mean, I'd like to think of these tree decompositions as maps from the graph to a tree, but they're not quite, right? Because the vertices are not mapped to vertices. But eventually, we will really think about maps from graphs to trees in certain sense. But the classical definition of tree decomposition is this. And the graphs which admit good tree decompositions are tree-like in some sense and very useful both in structural graph theory and from algorithmic point of view. And a good tree decomposition means a tree decomposition of low width, where width classically is maximum size of a bag, so of a pre-image of a vertex of a tree, -1 versus -1 is a bit artificial, but it's due to the fact that we want trees to have tree decompositions of width 1. And tree width of a graph is the minimum width of tree decomposition. So graphs of small tree widths are simple in certain sense. So what prevents a graph from having small tree widths? There are many answers to this question. And the answer which we will care most about today is a Bramble, which provides a very tightly connected dual concept to tree decomposition of a graph. So a Bramble is a collection of subsets of vertices. So it's the pink subsets on the right, so that the subgraph induced for each of this subset is connected. And for every, they're allowed to overlap those subsets. And for every 2 of these subsets, the subgraph induced by union is also connected, which means either these 2 subsets intersect or there is an edge between them. A heating set for a Bramble is a collection of vertices that contain the vertex from each set in a Bramble, and the order of the Bramble is the smallest size of its heating set. So if you can pierce the Bramble by a few vertices, it's not very complicated, but if you cannot, it's complicated. An example of a Bramble, a simple example of a Bramble would be in a complete graph, you take a collection of all the vertices. Then the union, the subgraph in every pair of vertices have an edge between them. So it is indeed a Bramble. And to hit all the vertices of complete graph, you need to take all of them. So in complete graph, there is a Bramble with the order equal to the number of vertices. And the tree width of a complete graph is number of vertices -1. You can just map all the vertices to one vertex. And so the theorem of Seymour and Thomas, which is at the bottom of the slide, says that Brambles really are abstractions to tree widths. So graph has tree widths at most, well, at least, let me say it as it's stated, at least k-1, if and only if it contains a Bramble of order k. This -1 is really this -1 that's subtracted in the size of the bag. Okay, so this theorem has a trivial direction, fairly trivial direction, and fairly non-trivial one. And I will mostly be interested in actually generalizing the trivial direction of this theorem. So only understanding how trivial things works in higher dimensions. So which one is trivial? Is that if you have a Bramble of order k, your tree width must be at least k-1. Why is that? Because if you think about it, there must be some, however you have a tree decomposition, there must be some bag which is a heating set for the Bramble. Because if no bag is, so you look at a particular bag, if it's not heating set of the Bramble, then there is a set in the Bramble that is completely in a subtree for on one side of this bag. But then there's can only be one side that has this property, and that points you towards this side. So there's always a bag which is a hidden set, and in this example, here it is. So the bag CDE contains a vertex from each set in the Bramble. Okay. So to generalize these results and this duality, at least partial duality, to one dimension higher, we will want to work with actual maps and with continuous maps, which might be not very agreeable for discrete mathematicians. In fact, we eventually, the theorem which I will state for continuous maps is proved again in the discrete setting. But this translation, discrete to continuous and back, is complicated enough that it's easier to just state and pretend to think in a continuous setting. But I will do some switching. So to make things continuous, we look at metric graphs where every edge is really a real interval joining the corresponding vertices. We don't really need to be graph to be metric. We only would need the topology of it. So the length of the edges don't matter. We think of two objects which are topologically the same as being the same. There is a way also of saying what a fairly equivalent of saying what a continuous map is. A continuous map from one graph to the other, if you allow to modify somewhat the graph on the bottom, insert extra vertices, will map vertices to vertices, and will map edges now not to edges, but to paths between the corresponding vertices. So I looked, on the right, we've drawn a tree corresponding to the tree decomposition of the graph on top previously, and I've selected only one vertex in the tree for every vertex of the original graph. And now I put a path, unique path in the tree, joining every two vertices which used to be, which are joined by an edge of the original graph. I only put some edges to make it not too messy. Now, what properties does this have? Well, importantly, if a new path passes through some bag in previous tree decomposition, it means one of the at least one of the vertices corresponding to the ends of this path lives in this bag. So in fact, there will not be too many edges mapped to any particular point in the tree. So if there exists a tree decomposition of a bounded degree graph with bounded widths, then there exists a continuous map from the original graph to the tree, so that no point is covered too many times. Now, what is a Bramble now? I want to slightly modify a definition of a Bramble too. There is a definition of strong Bramble, which doesn't actually differ too much quantitatively from definition of a Bramble. So instead of for every pair of subgraphs in a Bramble, either having them intersect or having an edge between them, I will want every two subsets to actually intersect. If we look at a metric setting, it's actually kind of convenient to think that every set in the Bramble, so now it's going to be a subgraph, it includes vertices and edges, is not only the subgraph induced by vertices previously, but also includes half edges reaching out from the set. This way, if two sets in Bramble had an edge between them, these half edges would touch and the result will be connected. So I also, in the definition in this slide, I reformulated the notion a little bit by requiring not only each subgraph to be connected and the union of every pair to be connected, but the union of every collection to be connected. But that's the same, right? If the union of every pair is connected, then the union of any subcollection is connected. And here is a lemma, which in some sense is a restatement of the easy direction of the Seymour-Thomas theorem from before. So previously we had a Bramble, there will always be a bag intersecting which hits every set in a Bramble. Now, if we have a continuous map from a graph to a tree and we have a strong Bramble, then there is some point which is in the image of every set in the Bramble. And now, how do we understand this? So let me look at the previous picture. Now it's not, now I changed the Bramble to have a strong Bramble corresponding to the three sets. Now it's not true that there is a bag that contains vertices from each three sets. But if I look at the images of edges of the path ACD in the red set, the edge BG in the green set, and the edge GE in the blue set, then the images of these three edges, they belong to the corresponding sets in the Bramble, and they all have a point in common, that bag that has a purple circle. And so previously this easy direction was kind of trivial, and this lemma is even more trivial, because the image of any connected subgraph is connected. And therefore it's a subtree of a tree. And if you have a strong Bramble, so it means that every two of these subtrees have a point in common. And all we want to say is that if every pair of subtrees have a point in common, then they all do. And that's not a hard result. You can prove it, say, by induction. It's an exercise for a graph theory class on trees. Okay. So that's the setting that will generalize. So now I will go up a dimension. And so what happens up a dimension? Now, instead of graphs, I will have simplicial complexes, two-dimensional. Means they have not vertices and edges, they have vertices, edges, and triangles. And for the purposes of looking at continuous maps, I will want to think of all of these objects as metric, or at least having an appropriate topology. So I glue in intervals for edges, and I glue in real triangles, which correspond to disks for triangles. But also, also one can think about abstract simplicial complexes, but then it takes a bit more effort to define continuous maps there. So vertices must be mapped to vertices, edges to paths, but then triangles must be mapped to disks, which one needs to define appropriately with the right boundary. So I want an analog of the previous lemma. So I need to define a bramble and I need to define a tree. Both of those things are not, there are different ways of generalizing it. Bramble is pretty simple. A bramble will be a collection of subcomplexes of the original complex, so subcomplex instead of subgraphs, so that the union of every collection is now simply connected. So instead of, I'm just replacing notion of connected here by simply connected. And what does simply connected mean? Here by simply connected, I will mean, first of all, the graph, so the one-dimensional skeleton is connected. And secondly, that whenever I have a cycle in this graph, there is a disk in the complex, so that this cycle is its boundary. So every cycle bounds a disk. That's the definition of simply connected. Or in a sense, you can contract every cycle. So sphere, a plane is simply connected, sphere is simply connected, torus is not simply connected. Now, what is a tree? So let me define first, all of the notions in 2 dimensions will be in some translations of notions in 1 dimension. So here is one definition of a tree. A tree is something that could be collapsed to nothing by repeatedly deleting leaves, vertices of degree 1. So that's going to be our definition of a tree. What is a leaf? A leaf will be a free face. So it will be a vertex or an edge that's contained in a unique maximal face. So it's either an edge in no triangle or an edge in a unique triangle or a vertex in a unique triangle, something like this. And so that's an analog of a leaf. And we can remove leaves repeatedly. And the complex is collapsible if you can completely collapse it. If you can completely delete everything by removing these free things. So here is a different, let me perhaps restate it in a couple of different ways. Another way of saying that a complex is collapsible, or at least the property it has, is that its triangles are linearly independent. So if you think of them as vectors over Z2, vectors of vertices, vectors of edges, then there's no collection of triangles that includes every edge even number of times. Because you can one by one remove these triangles by removing an edge that's only in it. And that's actually what we are going to be using. Same, a tree is a graph is a tree or a forest, if and only if its edges are linearly independent as vectors of vertices. There's no collection of edges that includes every vertex even number of times, a cycle. Okay, and now the main theorem so for the rest of the talk, I will try to explain that this is a good theorem, try my best to convince you, which is an analog of the previous lemma. So let X and Y be 2-dimensional simplicial complexes, so that Y is tree-like in this sense, is collapsible. let X be let F be a continuous maps from X to Y, and let B be a Bramble. Then the images of all then there's a point that's in the images of all subcomplexes in the Bramble. That's an analog of the previous lemma. Now, I'm not going to tell you the proof. It's not trivial anymore, at least not for me. It's not long, and it's obtained by taking a simplification of a proof of a theorem of Gromov. So, and restating it in some way. So, I think this is a new theorem, but unfortunately, I cannot verify it because I don't actually understand the Gromov's proof of his theorem. Not only I cannot understand it, I cannot completely locate it in the paper. All I know is simplifications, which have been in different papers, and those simplifications could lead to a proof of this theorem. Now, the proof of this theorem is not long and not particularly advanced. So it's about a page long, but I am not going to tell it today because it really, even though it's not long, you need to convince yourself and kind of accept into your heart certain basic things about behavior of cohomology. And I mean, right at this point, I mean, if you are combinatorialist like me, you need to overcome quite a bit of resistance inside yourself to just, you know, start work. I mean, it is just because it's cohomology doesn't mean it's complicated. It's some basic facts about how boundaries, co-boundaries of co-boundaries behave. But verifying those, making yourself believe those facts and making yourself manipulate with them takes some effort. Okay, so that's the theorem, and let me spend some time trying to justify to you that it is a theorem that, I mean, has certain applications. So the motivation behind it that I have presented so far is that it is an analog of kind of a trivial direction of a theorem about trivets and Brambles. First of all, here is a useful application of Van Kampen's theorem. But again, it's not that hard to verify by hand, which allows it too easy to verify that something is a Bramble in a simpler way. So something is a Bramble, again, instead of verifying it for any subcollection of sets in a Bramble that the union is simply connected, one needs to verify only a few simpler things. One needs to verify that every set in the Bramble is simply connected, that intersection of any two sets is connected, so just connected as a graph, and that intersection of any three sets is non-empty. Okay, so that's equivalent definition of a Bramble. If one can, I mean, if you think about what would it mean for any cycle to boundary disk, somehow one can reduce it to this fact. But it's a consequence of a well-known topological theorem. And here is a way now to derive, say, here's an example. Helly's theorem is a consequence of this new theorem when when you look at when y is just a plane, so any simplicial complex that's representable in the plane is collapsible. You will always have an edge that's on the boundary, that only belongs to one triangle. So a plane is collapsible. So if you apply this theorem to when y is a plane and the map F is trivial, I always wanted a theorem. I mean, that's kind of a faint. That is a theorem about maps that is non-trivial for trivial maps. And that's an example of such a theorem. It's known for trivial maps. It's not, it's already, the theorem as stated is known for trivial maps, but it has substance. So for a trivial map, this theorem implies Helly's theorem. So if you have now a collection of convex subsets, when do they form a Bramble? Well, I need intersection of any two of them be non-empty. If it's non-empty, it's connected because non-empty it's convex. Non-empty convex set is connected. Intersection of any three of them to be non-empty, and then it's a Bramble, and then intersection of all of them is not empty. So Helly's theorem follows from this theorem. So that's first motivation. Our second motivation is the main original motivation and comes from stack numbers. So let me start working in that direction. So I want to define now an order of a Bramble, and it will be somewhat different than order of a Bramble originally. So okay, so a hidden set of a Bramble would be a set of triangles. Now, for one dimension lower, it would be a set of edges, which is not quite the same as a set of vertices. The translation is not perfect because to make the translation, I use bounded degree. And so a hidden set for a Bramble now in 2 dimensions is a set of triangles, and order of the Bramble is going to be the smallest size of a hidden set. And let me define overlap, topological overlap of simplicial complex X over Y as the minimum over all continuous maps from X to Y of the number of triangles which cover of the maximum number of triangles which cover a point. So that's Gromov's definition of topological overlap. So we are minimizing over continuous maps, and then for a continuous map, we are maximizing over a point, looking at how many triangles cover this point. In particular, if point is covered by a vertex, it's covered by all triangles containing this vertex. That's our interpretation. And now the previous theorem says that for safety, I need my 2-dimensional complex to be pure, means every edge actually belongs to a triangle. If I have 2 simplicial complexes such that the image is collapsible, so tree-like, or say R2, and I have a Bramble in the pre-image complex, then the overlap is at least the order of a Bramble. And that's immediate consequence of a previous theorem, because for every continuous map, there will be a point that's covered by everything in the Bramble. So the set of triangles covering this point will be a heating set. So it's so the size of the set of triangles will be at least the order of the Brambles. It's just a reformulation of previous theorem, a bit compactified, so I don't have to say continuous map every time. Okay, so that's a bit of preparation. And now let me start on the motivation which comes from stack numbers. So stack numbers, that's the topic that started it all. It's they're also called page numbers. They're of interest, again, in computer science and structural graph theory, a measure of complexity of a graph. And the stack layout of a graph is an ordering of vertices and together with a coloring of edges phi in S colors, so that when you look at any color, it forms a stack, which means you don't have a pair of crossing edges. So for no pair of edges of the same color, they cross. And the stack number is the minimum S, so that there is such a layout. So there exists an ordering and coloring of edges, so that every color forms such a stack. And this figure, so by the way, there's whenever there is a nice figure in my presentation, I stole it somewhere. So one of my co-authors did it, or I found it on the web. I mean, some of my co-authors could do amazing pictures. Whenever the figure looks awkward, I did it. So I like this one. So it shows a grid, a strong product of two paths. So it's a grid with all the diagonals inserted, and it's 4-stack layout. So it's not that hard to see that actually any grid with all diagonals has a 4-stack layout, and that's what's shown in the picture. And here is a theorem. The main theorem, which is derived using the machinery of this paper, is that if we take a strong product of 3 paths, so now we're in 3 dimensions, it's harder to draw. So you take a kind of a Rubik's Cube and in 3D grid, and you insert all the diagonals in all the faces and all the cubes. So you'll get this 3-dimensional graph, still bounded degree. Then the theorem says that stack number of this graph, n by n by n grid, is on the order of n to the 1/3, exactly of this order. I mean, that's somehow it's a bit surprising to me that we were able to determine the order of the stack number precisely, where the original goal was to prove it's not 10, it's bigger than 10, say. That's already difficult. In fact, so to prove that it's at least of order n to the 1/3, we don't need all the diagonals. Hence, this picture is not too clustered. All we need is to take a face of every cube, every face of every cube to the 2-dimensional face, and put a diagonal in it. But we do need to put some diagonals. If we just take Cartesian product of 3 paths, we get a bipartite graph, and that actually has bounded stack number. So diagonals do matter. Okay, let me say a few things why this theorem, what are kind of features of this theorem. It uses this topological result, topological method, and it really seems to be a new method to lower bound stack numbers. As far as I know, all previously existent methods were based on either counting. There are not that many graphs with bounded stack number, way fewer than all graphs. So then by counting, one can say that a random graph with certain properties has big stack number. Or on density, one stack doesn't have too many edges, and therefore the graph with small stack number doesn't have too many edges. Or recently, a group including some of my co-authors on this paper, so Vida Djumovic, David Epstein, Robert Hickenbottom, Pat Mohan, and David Wood, they used Ramsey type arguments to prove a lower bound on stack number. But this is different. And this is a first example of graphs with bounded, explicit examples, so not based on counting. Family of graphs, bounded max degree, unbounded stack number. And it's also the first family that I know of graphs with still bounded max degree and fairly sparse structure, so strongly sublinear separators, so not expanders basically, and unbounded stack number. So it has nice features. It's not just a kind of a unique example for which we can compute stack number. Okay, so how do we prove this theorem? So the goal is to use Brambles. So what is the two-dimensional simplicial complex that is that underlines this picture? Well, let me take a Cartesian product of three paths, and now let me glue in all the faces of the cubes and nothing else. And I do it to make it simplicial by adding diagonal in every face, one, and then gluing in all the triangles. So that's going to be a two-dimensional simplicial complex. The complex itself depends on how I put diagonals, but topologically it doesn't. Really, topologically, what I get is the following. Take a n by n by n Rubik cube and make a paper model of it. So just make the sides and everything, make the 1 by 1 cubes just a boundary of paper and glue them together. So that paper thing is what we look at. And it contains a Bramble of order at least n. And this complex. And that's lemma. If you think about it, if you know about Brambles in grids in one dimension lower, then it's a very natural Bramble. So let me talk about things one dimension lower. Look at n by n grid now as a graph. So look at the front face of this picture. And I want a Bramble there in our previous sense. So a collection of connected subgraphs so that every two, say, share vertex in common of high order. So what do? I'll take every sets in my Bramble will be a union of row and column for every pair. Then each of them is connected. Every two share vertex in common. So it's a Bramble. And the order of this Bramble is, if your grid is n by n, is n. Because to hit everything in the Bramble, you need to either hit every row or every column. Because if you miss a row and column, you miss a certain Bramble. So in 3D, it's the same. Let me take every plane in this direction, and in each of three possible directions, and take their union. So take unions of any triple of planes in each direction. And you can check it's a Bramble. And clearly it has hidden size n. You need to hit every horizontal plane or every vertical plane or every, well, there are two types of vertical planes. So by previous theorem, therefore topological overlap of this grid n to A2 or to any collapsible complex is at least n. And that's tight as far as I can see, maybe with error 1 or 2, which bothers me. I couldn't get rid of additive error of 1 or 2. Because take my paper Rubik's Cube, right? And just smash it down linearly. More or less, all you have is n horizontal planes go on top of each other and not much else. So it's really tight with small additive error. Okay. Now, how does this relate to stack number? So I have this complex made out of triangles. And now I know that however I map it to the plane, there will be point in lots of triangles. Because degrees are bounded, I can make this triangles vertex disjoint. And now let me look back at my stack representation. So I put my points on the line and I draw my edges in different colors. I can also put my points on a circle and draw my edges as straight lines. Then I'll get lots of vertex disjoint triangles, if I want, that all share a point in common by this overlap theorem. And from that, I want to derive that there are many colors. If there are no crossing edges of the same color, I want to derive that there are many colors. And that's a nice lemma as follows. So I have triangles, which are now honest linear triangles, with all vertices on a circle. So I closed up my line in a circle. And I assume that edges can be colored in k colors, so that no two edges of the same color cross. Then the number of triangles is at most cube the number of colors. And why is that? Because that, so let me fix a point on a circle and let me order the edges, order the vertices, and so the edges in the order they appear on the circle starting from this point. And I want to prove now that no two triangles can have exactly the same color, same triple of colors in this order. And that's simple, it's simple case analysis. So suppose I have two triangles with the same colors. So I have two blue edges, they don't cross, so maybe they are arranged like this. Then there are two green edges, they don't cross, so maybe they are arranged like this, but then red edges have to cross. So that's it. Okay, so now let me recap. So that's the whole proof. So we prove that overlap of this n by n grid to R2 is at least 10. So we find lots of triangles in our map. So what is actually a map of this whole complex? Well, corresponding to stack number. We know where vertices are mapped, and the rest is affine. So the triangles, the edges and triangles are mapped affinely, linearly. And then we find, so we find lots of triangles with a point in common. We make them vertex disjoint by just greedily selecting vertex disjoint set because degrees are bounded. And then because the So we get about n triangles because we can count them in k colors, stack number of colors, so that they are non-crossing. The stack number must be at least cube root of the number of triangles, so on the order of n to the 1/3. Here is, I mean, I was very surprised, so that's it's tight, that you can actually, that there is actually a layout using n to the 1/3 colors that uses the following theorem. In fact, it's a more general theorem, but I state it this way. So let G be a graph with small stack number, but in fact small dispersible stack number, where we want individual stacks not only be non-crossing, but also be a non-crossing matchings. We don't want two edges at one point. If graphs have bounded degree, it's easy to make any stack layout dispersible by just also imposing proper edge coloring. So dispersible actually doesn't matter so much, but to make theorem correct, I need it. So let you be a graph with small dispersible stack number and chromatic number at most 4. In particular, a strong product of two paths has this property. It has chromatic number exactly 4 and bounded stack number and bounded dispersible stack number. Then if you multiply it by extra paths, you multiply the stack number by at most n to the 1/3. And let me try to explain by picture the magic of this proof. You do the following. You take the 4 coloring, you take the dispersible stack layout of the grid, and now you are multiplied by paths, so you'll insert paths locally. For every vertex, you insert paths locally. Now, what's the problem? Suppose I just honestly replace every vertex by a path. Then that will have lots and lots of intersections. If I have two paths in the same order and a matching between the two, right, an edge will blow up by a matching between corresponding paths. Then in this matching, every edge will intersect every edge. So if you take two disjoint paths and join every vertex to corresponding vertex in the other path, they will all cross. It's very bad. But what we'll do is put the paths for different colors according to different permutations, so that permutations for different colors are actually very unlike each other, don't have a lot of crosses, don't have many common subsequences. In fact, the common subsequence of order n to the 1/3. And this way, it will result in the right stack number. So somehow this topological argument actually does lead to the right bound. But I mean, the bounds from different sides are very different. Okay, so that was part about stack number, but let me give you even more motivation. So let me tell you about Gromov's theorem, from which we originally derived the required result. So this lemma about overlap greater than to R2, that it's at least n, we had it at least constant times n instead, and we derived it from the theorem of Gromov, which is more general, but it's the following. Let me look at a complete two-dimensional simplicial complex with n vertices. So I look at n vertices and I glue in every triangle. So I have all the triangles there, and choose 3 triangles. Then Gromov's theorem says that if I map this to R2, there will be a point which is in the images of 2/9 of all possible triangles. And that's tight. 2/9 is the right constant. In particular, it implies the following earlier theorem of Boros and Furedi, which, I mean, still for affine maps, that if we have a endpoints in R2s and some, and just look at affine triangles, so triangles, all triangles which are formed by vertices in P, then some point will be covered by 2/9 of all those triangles. But as far as I know, for continuous not affine maps, the only known proofs are variations of the Gromov's argument. And so is the one which I'll tell you now. I mean, it's also just an interpretation of Gromov's argument. So let me show you how to prove it using Brambles. So to prove it using Brambles, I need to show you that there is a Bramble in a complete two-dimensional simplicial complex with of order about 2/9 and choose 3. And here is a Bramble. It's not the most elegant, but as far as I know, I mean, I convinced myself that it has to be something like this. So Brambles actually can recover this result. So we do the following. We look at collection of all graphs, first just graphs on n vertices, which have at least 2/3 n vertices in them, and which expand very well. Whenever you take a set of at most half of the vertices of your graph, at least half of the possible edges from the set are still in G. And possible edges, I'm not counting just from X to the other vertices in X, but I counted from X to all the other possible vertices. So it's a technical definition. That's a collection of graphs, and my Bramble would be all cones over these graphs. So I'll take my simplicial complexes will be, I take an extra, for each this graph and each extra vertex, I cone it. I take all triangles containing edge of this graph and this new vertex. So I have a bunch of cones. Now, clearly, if you think about it, any cone is contractible. You can contract it to the top vertex and so simply connect it. So I need to check that the intersection of, to show that it's a Bramble, that intersection of any two is connected, intersection of every 3 is non-empty. That's easy. Intersection of every 3 is non-empty because number of vertices is bigger than 2/3. And intersection over 2 is non-empty. It easily follows from second condition. A difficult part, a slightly difficult part is to show that the order of the Bramble is 2/9 and choose 3, but it's true. And that recovers Gromov's theorem. In fact, it recovers that overlap from delta n to any collapsible simplicial complex is at least this much. And I don't know, I mean, I don't know if Gromov can prove this. Presumably he can if he tried, but I couldn't see any statement that would imply this for collapsible complexes. He needs for him, he needs manifolds, which is a different type of beast than collapsible complex. Okay, let me now move to conclusion with some open questions. So the theorem is true in higher dimensions. Brambles theorem is also, the Brambles theorem is true in higher dimensions. I just didn't tell you this because I didn't want to define what simply connected means. For those of you not opposed to cohomology, I just need to all cohomologies to be, all meaningful cohomologies to be trivial or homology equivalently. So Brambles theorem is true for higher dimension, and Gromov's theorem, right? It's important for higher dimensions. It says that if you take a complete simplicial complex on n vertices and now look at all d-dimensional faces, then there is a point covered by a positive fraction of all, and you take a continuous map to ID, there's a point covered by positive fraction of all d-dimensional faces, and positive fraction is roughly 1 over d factorial. It's known by a result of, sorry for the misspelling, by Buch, Matuszek, and Nivash, that this constant cannot be improved by more than d plus 1 factorial over d plus 1 to the d plus 1, so roughly e to the d. But there's a big gap between 1 over d plus 1 factorial and 1 over e to the d. And the question is, can we actually improve this by doing Brambles? Unfortunately, I don't understand higher dimensional topology enough to even produce a Bramble that matches Gromov's bound. But I don't know that you cannot beat it. I can prove that there exists a Bramble proving a non-zero constant. So Gromov's theorem with non-zero constant can be proved using Brambles. In particular, Gromov's theorem is true for any collapsible complex, if that matters, any tree line. Second, let's go back to the Trivets motivation. So what can I do in a Trivets-like world, compared to 3D compositions in two-dimensional case? What about the actual meaningful direction of Seymour-Thomas theorem? That direction says that if you don't have, at least in my setting, a nice map to a tree, then you have a Bramble that shows it. Is that true, at least in some sense? Suppose you have a pure, let's say, two-dimensional simplicial complex that has big overlap to very big to every two-dimensional simplicial collapsible two-dimensional complex. Does it always come from a Bramble? Are Brambles really abstractions? Secondly, there is a grid theorem. Right now, we're getting really into a meaty parts of the graph structure theorem. Do Brambles always come from grids? I showed you a Bramble in a grid, but is it true that any two-dimensional complex with a Bramble of high order contains a large grid-like subcomplex? I don't know. That seems very hard, right? Grid theorem is not easy to prove. Here, I don't even know, and it needs a notion of mine or something. I don't even know what the right notion is. Secondly, overlap to the R2. So let me do this separate. Is different. If you look at overlap to the line 1 dimension lower, if you look at graphs which have high overlap when you map to the line of bounded degree, let's say, then they're not the same as large Trivets. They have large path widths in a sense. So there are different abstractions, not just Brambles, also trees. What abstractions not to Trivets in 2 dimensions, but to path widths in 2 dimensions, which now are not path widths, but plane widths? There should be something else but Brambles, but I don't know what. Okay, and that's all I wanted to say. Thank you.